Hello. Um, Here's a video about something called the birthday paradox. And this was asked for by Stuart. Thank you, Stuart. Um, it's as it happened, it's not a paradox. It's just a surprising mathematical result. Let's have a look at this. It's to do with if you've got a certain number of people in a room, um, the probability, the likelihood of two or more of those people having the same birthday. So let's have a think about it. On the surface of it, if you've got 30 people in a room and just assume that it's a normal year of 365 days, then on the surface of it, you might think it's quite a low probability that two people would have the same birthday. Let's have a look at the problem. Now, before we start, I just want to do a small uh, little mention of notation, and that is factorial notation. If we say something, so factorials, factorial is what we're thinking about. So if you've got an integer n, we're talking about n factorial is what we say. And that, for example, e.g., if you've got 4 factorial, that means it's the notation for 4 times 3 times 2 times 1. That's all it means. So if you've got a general number n, that means you've got n times n minus 1 times n minus 2, dot, 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 all the way down to 2 times 1. So, for example, again, if you're asked to calculate maybe 5 factorial over 3 factorial, then you could write it out in full. 5 times 4 times 3 times 2 times 1 times 1. And all of that would be divided by 3 times 2 times 1, 3 factorial. And you can see this part would cancel, and you end up actually with just 5 times 4, which is 20. So you could have calculations like that. Right, let's have a consideration about this two people having the same birthday. Now, that is quite, if you think about it, there's quite a lot of things that you need to do to check that. You need to choose one person and then go through and check the other 29 to see if they match up and make a pair. And then you have to do it again for the second person and so on. So that is too much calculation. There is another way of considering this, and that's to think about the complement of the question. So it's almost like saying the opposite of the question. What's the opposite of if you've got a room full of 30 people and you're trying to think about two people might have the same birthday, then it might be easier to think about what's the probability of nobody having the same birthday. So let's have a think about that. The probability that no one has the same birthday. Now, because these are complementary to each other, then they must add up to 100% certainty. So we can say the probability of two or more people have birthdays, that must equal 1 minus the probability no one matches birthdays. No one matches birthdays. So let's just think about that then. So we're just thinking about the probability no one has matching birthdays. And one way we can start with problems like this is to simplify them a bit. Instead of thinking about 30 people in a room, maybe think about 2 people in a room and ask if their birthdays match. So 2 people in a room. Let's see. So we want the probability that they don't match. So for the first person, so we've got 2 people, person 1 and person 2. And we're saying that the first person can have any birthday they like. So that's 365 days out of any of the 365 days. And then the second person, well, the first person has chosen a day already, say January the 1st. So the second person can have any day except for January the 1st. So 364 over 365. 365. And then we're done. So this would be the case for two people. And then if we wanted to work out the probability they have the same birthday, we could take this away from one to get the answer. So that's for two people in a room. So let's go straight from there to 30 then. 30 people in a room. It's going to have the same form, the same pattern. Room. So 30 people in a room. Probability no match. No match. Equals, so the same for the first one, 365 over 365. And then the same for the second one. Yeah, the second person can choose 364 out of 365. And then the third person, well, these 2 days are different. The first two people's days are different. So there's only 363 left to choose out of the 365. And you can see we can keep doing that. And if we want to work out the last one, that's the first, the second, the third. So in the end, we need to do 365 minus 29 is 336 over 365. So this is the calculation that we need to do to work out no match for 30 people. So let's consider, well, let's rewrite it. So no match, the probability no match equals, so we've got on the top, we've got 365 times 364 times dot 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 down to 337 times 336, and that is all over 365 times 365 times dot 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 365 times 365, and in total, I just want to make the observation, there's 30 terms. 30 terms. So now let's consider the denominator first. Denominator. If you consider the denominator, we've got 365 times dot 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 times 365, and there are 30 of these terms. 30. So we can write that in index form, so 365 to the power 30. So that's the denominator. Now the numerator is a little more complicated. Numerator, we've got 365 times, and then they're going to go down, 364 times dot 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 all the way down to 337 times 336. Now, why don't we rewrite it in a way, this is actually going to end up going in the calculator. So this is long, so we need to make it into a way that the calculator can understand, in maybe using factorial notation. So on the top we've got 365 dot 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 down to 336, and then why not multiply this by 335 times 334 times dot 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 all the way down to 1. And then if we're doing that to the top, we need to do the same to the denominator. So if we do 335 times 334 times dot 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 all the way down to 1, then we can now rewrite this. On the top, we've got 365 all the way down to 1. So that's 365 factorial. And on the bottom, we've got 335 down to 1. So that's just 335 factorial. So now we can write down the probability no match equals So it's 3 on the numerator, it's 365 over 335. And then in the denominator, we've just got 365 to the power 30. Now, in school calculators, even though there is a factorial button somewhere, there it is there, the numbers are too big for the calculator. However, the calculator on any computer is fine if you just go to the scientific mode. There's a factorial button there, and that will go in quite easily. And if you put it in, you end up with 0.2937 4 dp, 4 decimal places. And so then we go back to the original question, which says, what's the probability of 2 or more birthdays? Well, the probability of 2 or more birthdays is 1 minus this probability here, 0.2937. If we put that into our calculator, we're going to get 0.7063 or 70.6%. And that's the answer to our question. But let's just consider this in the context of what it's saying. It's saying that if you have just 30 people in a room, there's a really good chance that there's going to be 2 people or more with a birthday, which is just a slightly surprising result. Intuitively, you might expect it to be a lot less than that. But there you are. So, thanks again, Stuart, for the question. See you all next time.